Hi everybody, welcome to chapter 13. Now we're going to talk about vector functions and space curves. Now in Calculus 2 we introduced this idea of a parametric equation, and we said that this was for some equation that could not be written in the form of a function. So if I have this two-dimensional plane here, and I have the x-axis, and I want to write y as a function of x. I want to say that, okay, y is going to be a function of x. What that would mean is that would give me a series of unique outputs for each input. So every x value on this curve has a corresponding output, f of x, and gives a unique y value. And we can see the issue when we have a curve C that looks something like this that fails the vertical line test. That means if I draw a vertical line at this point right here, there's no way that I can describe this y as a function of x, because for this value of x, we have three different outputs. And for that reason, we bring in this third parameter called t. Now what we can do is we can write x and y as a function of t. So we no longer have y as a function of x, but we have each of these variables as a function of t. Bringing in this third parameter really just means some variable of t. Now t doesn't necessarily have to mean time, but we just, for the most part, you'll see t being used because it can mean time, so this just translates over to physics. But we can write this as any variable, so this could also be written x and y is equal to f of s comma g of s. It does not matter what that parameter is. And much like in Calculus 2, we are going to be going from the equation form to parametric form of some vector, eliminating this parameter t, and sometimes writing this in the form of that third parameter t, or in 3 dimensions t is going to be that fourth parameter. Now for vector functions. So in 2 dimensions, if we think back to Algebra 1, we know that the domain is the set of all possible x values, and the range is a set of all possible y values. But what happens in 3 dimensions? In 3 dimensions, we no longer have an x and y, so we no longer have this horizontal input and vertical output, but now a vector valued function, or a vector function, is just a function whose domain is a set of real numbers and whose range is a set of vectors. All right. This is going to be particularly useful in these 3-dimensional vectors. All right, so this means that for every number t in the domain, there is a unique vector in V3, just in 3 dimensions, denoted by r of t. So now we have this other parameter t, and we can rewrite this r of t, this vector, in terms of t. Now we don't have an x, y, and z. We have an f of t, g of t, and h of t. In this case, just using the t to denote that independent variable. We can use any other variable that's not x, y, and z to denote that, but you will see t used most frequently. So in this first example, we are just asked to find the domain of this vector function. So how do we know what inputs of t are valid? Well, we have 3 different components, so we're going to separate this into our 3 components. So we're going to look at t cubed, the natural log of 3 minus t, and the square root of t. And we want to know for which values of t is this vector function defined. So what about t cubed? Well, what is the domain of t cubed? Well, we know that this can be all real numbers from negative infinity to positive infinity. What's the domain of the natural log of 3 minus t? Well, we know that you can't take a natural log of a negative number We also can't have the natural log of 0, so that leads us to the conclusion that 3 minus t must be greater than 0. If that's the case, by adding t to both sides, we get that t must be less than 3. So t must be less than 3 for the y component to be defined. Now for that z component, the square root of t, well, we can take the square root of 0, but we cannot take the square root of a negative number, at least not in the real number system, and so t must be greater than or equal to 0. So how do we ensure that all of these conditions are true? Well, we can draw a number line. So on our number line, let's mark all of the points of significance. So we've got 0 and 3. And because now we have one variable, one parameter in all 3 positions, so to describe all 3 components, we're just finding the values of t that are going to make all components of this defined. So we need to include all 3 components. We're going from negative infinity to positive infinity for the first component. We're going t is less than 3 for the second component. This open circle meaning exclusivity. T must be less than 3. And for the third component, t must be greater than or equal to, filling in this circle for inclusivity, so it must be greater than or equal to 0. Now we said because we have this one parameter, then all of these must be true. So where do these overlap? Well, they overlap from 0 to 3. In this case, we are including 0 and excluding 3. So this is our domain. And because we can see that now our vector r is a function of this parameter t, now that we found the domain, we could use this domain to then find the range, but we are not going to worry about that. The important thing to note here is that the range is a vector. The output of this is a vector function. All right, so now on to limits and continuity. So when we have this equation in parametric form of a vector, we know that the limit of the vector function is just defined by taking the limit of each individual components. So this just goes to show that this 3-dimensional vector function behaves much like a 2-dimensional vector function. Again, with that idea that calculus 3 is kind of like calculus 1 in 3 dimensions. So it's very true in this case. So to find the limit of this function r of t, let's find the limit of the individual components. So we're finding the limit of the x component. So we are taking the limit as t approaches 0 of 1 plus t cubed. We are taking the limit as t approaches 0 of t e to the power of negative t. And finally, we are taking the limit as t approaches 0 of the sine of t over t. Now we're just doing a little refresher on our limit laws. So to find an algebraic limit, the first thing I'm going to do is I'm going to plug this value of a into this expression. So to find that, I'm going to find 1 plus this value of 0 cubed, which is just 1. And if I get a constant like this, then I know that that is our solution. For the limit of the second component, when I plug 0 in for t, I get 0 times e to the power of negative 0, which is 0. I know e to the power of 0 is 1, and I know 0 times 1 is just 0. So the limit of that second component is 0. Now for the third component, when I plug in 0, I get the sine of 0 over 0. Okay, well, the sine of 0 is just 0. And when I get something in the form of 0 over 0, yes, that's right, we use L'Hopital's rule. And L'Hopital's rule states that if I have one of our indeterminate forms, in this case 0 over 0, when I evaluate a limit, then that limit is the same as if I take the derivative of the numerator and the derivative of the denominator. So when I take the derivative of the numerator and derivative of the denominator, I get the limit as t approaches 0 of the derivative of sine of t is cosine of t. The derivative of t is 1. So now let's try plugging in this value of a to our expression, and we get the cosine of 0 over 1. I know the cosine of 0 is just 1, and so our limit is 1. And so we've got our three limits. We've got for the first component, our limit is 1. Second component, our limit is 0. And for the third component, our limit is 1. So we can write this as in different ways because now our limit includes these three different components. So our limit we can write as a vector. If we write this as a vector in I, j, k form, we have 1i, 0j, and 1k. So we can write that as I plus k. We can also write that in the more classic form of that vector of our I, j, and k components. So we can write this as 1, 0, 1. So that's really all there is to limits. We're just remembering those old limit laws from the last two calculus classes. So now for space curves. Now space curves are very, very similar to vector functions. So we're saying that this space curve is the set C of all points x, y, and z in a space, where x is f of t, y is g of t, and z is h of t. So when t varies through this interval I, this is called a space curve. So C is really this moving particle C, whose time at t is given by this position, f of t, g of t, and h of t. So it's easier to describe this if we look at a graph. So if we have some space curve C, which is the path that some particle takes, then the position vector is just the vector from the origin to any given point. So C is this curve, and then that vector is just a straight line because we know that vectors have a direction and a magnitude. So this vector is in blue, it's just the distance between distance and direction of this point between the origin and any point on this space curve. And that's why when we talked about vectors, we said that we can write this equation in an infinite number of different ways, and that each value of t describes a different point on this curve. So for t is equal to 1, it might look something like this. This might be that vector at t is equal to 1, for example. So the space curve is the curve, the vector is the movement from the origin to any point on that curve. Okay, so now let's describe the curve defined by the vector. So we're talking about the difference between this space curve and this vector function. Well, this vector function r of t means my x component will be given by 1 plus t. My y component is given by 2 plus 5t, and my z component is negative 1 plus 6t. And we can write these in the form of parametric equations. We know that these just really describe the different components with this parameter t. Now what does this mean? Well, We know that a vector includes a point and a direction. We know that we have an infinite number of equations that can describe this curve. So for a point, we can find a point by just designating a value of t. Let's let t be equal to 0. If we let t be equal to 0, that means our x is going to be 1 plus 0, which is 1. Our y is 2 plus 5 times 0, which is 2. And our z is -1 plus 6 times 0, which is -1. So one of our points are 1, 2, -1. Now obviously we have an infinite number of points along this curve, but this is just one of our points. Our direction is going to be, for each component, the coefficient of t. So our direction looks like 1, 5, 6. And if we want to write that in the form of a vector, our direction is 1, 5, 6. It's essentially our rate of change in each of the x, y, and z directions. So how can we describe this curve? Well, we can say that this curve is a line that passes through (1, 2, -1) in the direction (1, 5, 6). So now for sketching parametric curves. So we want to sketch the curve whose equation is r of t is equal to cosine of ti plus sine of tj plus tk. So we have these three different equations if we parameterize this vector, right? So if we break it up into these three components, we have x is cosine of t, y is sine of t, and z is t. So the question is, what might this look like? Well, we're not used to seeing equations in parametric form. So to think about what this might look like, we can use this identity to go from parametric to just the regular vector form of this, of cosine squared of t plus sine of t squared is equal to 1. Because we know that this is true, we can do some substitution. This is equal to, well, the cosine of t is x, so we can say that x squared plus y squared is equal to 1. Because this does not involve t, we have some z is equal to t. And that can just be said that z is equal to anything. Before, when we did this in chapter 12, we just said that z is equal to some k if we're only left with x squared plus y squared is equal to 1. And in this case, if we have x squared plus y squared is equal to 1, comma z is equal to k, what does this look like? Well, this looks like a cylinder. A cylinder along the z-axis. All right, now let's look at another way to view this using the parametric equations. So if we're just looking at these different planes on the xy plane, if z is equal to 0, then like we said before, we have this circle, x squared plus y squared is equal to 1. If z is equal to k, that means we have a cylinder. See, for one value of z, a cylinder in 2 dimensions is just this circle. So now what about on the xz plane? Well, if we let z be equal to t, then x is cosine of t. Then we can plot this. Then we have this axis for which z is our independent variable and x is our dependent variable. Since x is cosine of t and z is t, then we have the cosine of curve, which starts at 1, and so it's going to look something like this. If we look at this from the YZ plane, then our independent variable can again be z. Our dependent variable can be y. And now we have a sine curve, which passes through the point 0, 0. And looks something like this. So now let's look at this in 3 dimensions. Well, on the xz plane, we've got the cosine curve. On the yz plane, we've got the sine curve. And in 3 dimensions, this is going to look like this corkscrew. Now looking at the non-parametrized version of this equation, x squared plus y squared equals 1, that means that this curve traces along this cylinder, x squared plus y squared equals 1, and we can see what it looks like on the xz plane and on the yz plane. So this is how we're going to, and in this case, for the purposes of this class, we're not really going to be sketching, we're just going to be matching a model of a 3-dimensional surface with the parametrized or non-parametrized equations. So just recognizing that this cosine and sine really just means that this goes around a cylinder. Okay. And we'll look more at curves. This curve is called a helix. It's just a special name for this curve that goes around a cylinder. We'll look more at curves like this when we do that next Mathematica assignment where we're graphing curves in 3 dimensions. So now let's move on to intersections. So we can find where 2 curves intersect. Now there's a difference between an intersection and a collision. So curves collide if the intersection happens at the same time. Curves intersect if an intersection happens but at different times. So when we talk about an intersection, if we think about a roadway, well, between 2 streets, where these streets meet, we have an intersection. However, it's only a problem if cars are in the exact same place at the exact same time. So that's when a collision occurs. So first, let's look at the intersection of 2 surfaces. So we want to find the vector function that represents the curve of intersection of a cylinder and a plane. And to find this, we're going to look at part B. To find parametric equations for the intersection of 2 surfaces, we are going to combine the surfaces into one equation. So my first equation, x squared plus y squared is equal to 1. My second equation, y plus z is equal to 2. So I want to combine these, and the best way I'm going to do that right now is I'm going to parametrize both of these equations. So if I do that, I'm looking for the x, y, and z components in terms of t, and I'm going to need to call something t. In this case, what if I let x be the cosine of t? And y would be the sine of t. Now, while this might seem strange, some of you might be seeing that pattern. Now, the reason I can do this is because I know that if z is equal to 0, when we're looking at the y and x axes, I'm going to have a circle with a radius of 1. So that's what this equation would look like if z is 0. I also know that I can describe that by calling my x value cosine of t and my y value sine of t. So that's just because I know that this describes a unit circle. Now what about z? Well, if x is cosine of t and y is sine of t, then I can find z by taking the sine of t plus z being equal to 2. And solving for z gives us z is equal to 2 minus the sine of t. Well, now we've got an x component, we've got a y component, and we've got a z component, taking into consideration both of these equations. And so our vector function that represents this curve, we can call this r of t, is equal to the vector of the first being cosine of t, the second component being sine of t, and the third component being 2 minus sine of t. And that's all there is to this equation. This one's a relatively simple problem. So let's look at one more. We want to find the vector function that represents the curve of the intersection of these two surfaces. The paraboloid, z is equal to 3x squared plus y squared, and the parabolic cylinder, y is equal to 5x squared. Now in this case, we have a coefficient in front of the x squared but not the y squared, so we can't describe this as a circle. But I'm remembering that my goal here is really to just describe this in terms of t. And I see this equation y is equal to 5x squared. Well, if I let x be equal to t, that means that I could describe x and y in terms of t. All right, so if I let x be equal to t, that means y is equal to 5 times t squared, well, which is just 5t squared. And if y is equal to 5t squared, x is equal to t, then I can use this first equation of that paraboloid to find z. And so our z is equal to 3t squared plus the quantity 5t squared. And so z is equal to 3t squared plus 25t squared. Now you might be saying, well, wouldn't it be easier to just call xt in this first example as well? And yes, we could absolutely do that, because remember we said that there are different ways that we can describe the same surface. So there are different equations we can use to describe the surface of this curve. So continuing on here, now that we have our x, y, and z components in terms of t, we could just write that vector function of r of t being equal to t, 5t squared, and 3t squared, plus 25t to the power of 4. Let's fix that. There we go. So this is our r of t. Now we have one more example. We want to find where r1 and r2 collide or intersect. We want to find those points of intersection and their time of collision. So now we're talking about some vectors. In these previous two problems, we were talking about this curve of intersection of two surfaces. So surfaces are going to be solid. So when we talk about two surfaces intersected, we want to look for that equation. When we talk about two curves colliding or intersecting, we have some time that this happens. So we're imagining that these have more to do with a traveling particle that is a certain place in a certain time. So we want to find their points of intersection and their times of collision if these occur. So let's look at their collision first, because to find their collision, we know they need to be in the same place at the same time, which means that the x component of r1 must be equal to the x component of r2. The y component of r1 must be equal to the y component of r2. And the z component of r1 must be equal to the z component of r2. So now that we have these three equations, if there is a collision, then there is some time t that will be a solution for all three of these components, for the x, y, and z components in this system of equations. So let's go ahead and try to solve for t in the first equation. Rearranging this, t is equal to 1 plus 4t. If we subtract t from both sides and subtract the 1, well, we get 3t is equal to -1, which gives us t is -1/3. So if there is in fact an intersection, then this time of -1/3 will be a solution for these other two equations. So now let's try to plug this into the second equation. And we get -1/3 squared is equal to 1 plus 16 times -1/3. -1/3 squared is +1/9, and is 1/9 equal to 1 minus 16/3. Well, we can see without actually solving that no, it is not. So this is not true. Because this is not true, there is no collision. There is no value of t that will be a solution for all three of these parameters. Because think about it this way, just because two particles might be in the same position in the x and y directions, if they're in a different position in the z direction, that means they're really just sort of floating above each other at a certain period of time. They need to have the same x, y, and z values for the same exact time for there to be an actual collision. So now what about an intersection? Well, for an intersection, they don't necessarily have to be at the same place at the same time. They just have to cross the same path at one point, meaning that we can have different variables. So for their intersection, we also have a system of equations, but now I'm going to call one of the variables s and the other t. So for R1, I'll stick with t. And for R2, I'm going to rewrite this in terms of s and just say that s is equal to t. So I have t is equal to 1 plus 4s. T squared is equal to 1 plus 16s. And t cubed is equal to 1 plus 52s. So now the time at which our second particle reaches a certain position can now be different than the time that the first particle reaches this first position, this certain position, now that we have two variables. So let's solve for this s and this t. Let's solve for t by plugging this value of t into the second equation. So if we do that, if we plug 1 plus 4s into the second equation, we get the quantity 1 plus 4s squared is equal to 1 plus 16s. Squaring this binomial, we get 1 plus 8s plus 16s squared is equal to 1 plus 16s. We subtract everything on the right-hand side to the left side of the equation, we get 16s squared. 8s minus 16s is -8s, and 1 minus 1 is 0. Factoring out that s, actually we can factor out an 8s, we are left with 2s minus 1. Using that zero product property, we get 8s is equal to 0, or 2s minus 1 is equal to 0. Dividing both sides by 8, we get that s is equal to 0. Adding 1 to both sides, we get 2s equals 1, and dividing by 2, we get that s is equal to 1/2. So now these are our two solutions. Now we have to check that they're true for the third equation. So we're just sort of verifying that the third equation is true for t cubed. Now, there are different ways to do this. Rather than cubing this initial binomial, what I'm going to do is we're going to plug these values of s into the first equation to find out what that t would be. So for s is equal to 0, t would be 1 plus 4 times 0, which is 1. So if s is 0 and t is 1, does that make this a true statement? Does 1 equal to 1 plus 0? Yes. Does that make this a true statement? Is 1 equal to 1 plus 0? Yes. Obviously makes this first equation a true statement. Now, if s is 1/2, what would happen in this first equation? 1 plus 4 times 1/2, well, that's 2, and so t would have to be equal to 3. So is that true for these other two equations? T squared would be 9. Is that equal to 1 plus 16 times 1/2? Yes, 1 plus 8 is equal to 9. Third equation, t cubed, well, I know 3 cubed is 27, and 1 plus 52 times 1/2 is 1 plus 26. Great. So this is true for all three equations. Let's just make a note of that here because we did that mental math. All right, so now that this is true, what are we looking for? We're finding those points of intersection. So it doesn't matter at what s and t values they intersect, it matters what those intersections are. And to find that, we can plug these values of t into the first equation, in the first vector, or we can plug these values of s into the second vector. I think it's easier to use this first one. So we have r1 of 1 is equal to 1, 1 squared, 1 cubed. And for r1 of our second value of t, which is 3, that's going to be 3 to the first power, 3 squared, and 3 cubed. And so these are the points of intersection. And because these are the vector form for the points of intersection, we should really put this as 1, 1, 1, and 3, 9, 27, because we want to make sure these are points. This would be the vector form, so this is just the distance from the origin to each of these points. And that is it for section 13.1.